So today's topic is that of slope fields. So slope fields, why do we need them? We need them because most differential equations can't be solved. I think I alluded to this in our introductory videos. So if we have a differential equation that can't be solved, or maybe it can be and it's just too expensive to do it, right? We need to throw too much computation time at it. What we can do instead is look at maybe a picture of what solutions tend to look like. And this would give us enough information to maybe make predictions, to build a model, or to just get the insights into a situation that we need. Right? A differential equation usually is talking about how something evolves over time, or how something changes in response to certain quantities being present. So maybe getting a more holistic picture is sometimes more valuable or just more bang for our buck. So this can often be enough to solve a problem. So we should integrate this into our course. So what can they tell us? Well, this is what a slope field can look like. They're little line elements that fill a plane. You typically have, your x-axis and y-axis, or your t and u-axis here. And at each point, you have a little slope element that tells you how things are changing at that point. And so mapping a solution curve, which is something we'll learn how to do numerically later on, methods for doing this, we can see that what tends to happen with this differential equation with some, y prime equals f of xy. This rule describes a scenario where the variables interact in this way, that based on some initial condition, this curve is heading this way. They seem to all be like funneling into this one trajectory here, right? Which that can tell you a lot. Right? That tells you a lot about this y value in particular, that this y equals 0. It looks like things, no matter where they start, tend to decay to 0 in this system or rise slowly up to 0. So that gives you a lot of bang for your buck without even having an analytical solution, without needing to go through finding integrating factor or do, any of the other methods that we've seen or will see. So a lot of information for not a big price, because we usually use a computer to do this. So how do they work? How do we get that type of picture? Since we're working right now with first order equations, so they're of this form or of this form, right? What we have really is a two variable function on the right hand side, right? The right hand side is some rule involving x and y, or t and u, and its output is what? The slope of the tangent line at that point for a function that would be passing through it. Okay, so we might not know the exact value since we don't have, a particular solution, but we know if we were here at a certain point in the plane, like over here, I know what the slope at that point will be. And here's another point, xy. I know what the slope at this point would be. I don't know if I'm there or not. Doesn't particularly matter. And over here, a point will tell me the slope, this y prime, at each of these. Does that make sense? So I've got a rule that at each xy tells me the slope. So we put this little slope element in there. Okay. So I'll show you how to do this by hand. This is not something we actually normally do by hand. You're going to do it once or twice. You'll do it once on a test, just a couple of points. But if you haven't seen already, this is grunt work, right? No one's doing this by hand, okay? This is work that's done for computers, but you need to understand the algorithm. You need to understand how we build this out. So if we remember an example that we have seen, memory fails me if we've seen this or not, the law of cooling we definitely played with. And let's take, all right, so we've got this ODE here where I've got some rule on the right of what? I've got some rule. Is this a rule of u and t? Yes, it's really just a rule of u. But we can assume implicitly it's a function of time too. Okay, so the right-hand side tells me the slope of the tangent line, or the instantaneous rate of cooling at any single point. So let's assume for this example that our scaling coefficient here is 0.2, and that the A of T, the ambient temperature, is oscillating between 5 and 15 degrees, right? Something like that? Yes, between 5 and 15 degrees. We don't need to get too excited about units or anything here. We're just proving a point, okay? So ambient temperature is oscillating throughout the day or throughout a period. K is constant. So if we knew, let's say, that at T equals 5, that our U equals 8, that the temperature of the object, okay, is 8 degrees. And this is our initial condition. Then what we would do is go in and compute U prime of 5. So T equals 5. So here's my K. Here's U of 5. We know that this is equal to 8. Right? We know that A of 5 is really this 10 plus 5 sine of 5 over 2. And we come up with a number. Okay, because I have this 0.58. I plug it into my rule, and I get the slope of a tangent line to a solution. If there's a solution there, that's what the slope would be, right, at that single point. And so we make a little mark on the graph with that slope of, 0.998. So almost 1 would be the slope here. So, what would I do? I'd come out here to 5 and 8. Here's 8. I would know out here at this point, I have a slope of 1. So I put this little tiny element in there. It can have an arrow on it signifying direction. It doesn't always have to. All right, but since this is a positive slope, right, we can assume that it is moving this direction. There's also some other ways you can tell. But I could do that as long as I had the points, right, any TU pair, I could figure out what this slope would be just by plugging these coordinates in and spitting out new slopes. And I could fill the plane with this information, right? Because I have a rule that can take any point in the plane and do this, assuming our domain is nice. So you'll do this a couple times, but really what we want to do is hand off all grunt work to a computer. So we say, hey, Mr. Computer, you do this. And this is what we should be looking at. This is for this particular problem. So 5, 8, here's 5, here's 8. Somewhere around here is our little slope element with slope of 1. Okay, and everything else has been done by the computer. It goes through each point and says, what's the slope here? Bink. What's the slope here? Bink. Right? You might be asking yourself, did we used to do this by hand, Mally, way back in the day? Yes, we did. And there's actually a slicker way to do this by hand using something called isoclines, where you find equations of lines where they all have the same slope, and you kind of trivialize a lot of the work. So you say maybe along this line or along this curve, we know the slope is all the same, and so you can make a lot of these dashes without having to do each individual point yourself, if that makes sense. But that's not something I'm going to go over really in this course so much. I do want you to know how these things are created, and so you should know that process. But for the rest, we're going to use this online tool that I'll link to you in a bit. Okay. So again, why do we care about this? We care about this because this can tell us about the behavior of a system without needing to actually solve for a particular or general solution. So with that, we're going to blast off into using this Direction Field Explorer and then doing this lab activity for the remainder of class. So I will link these things in the chat right now and pause the video. All right, so this is the Direction Field Explorer. You'll notice at the top, maybe I can zoom in a bit here. You'll notice at the top that you can change the names of the variables. So oftentimes we'll work with U and T, which can be nice. And here we'll input the differential equation, again, for first order equations on the right-hand side. So here, maybe we can just do the one we were working on, which was what? Negative 0.2 times U minus A was 10 plus 5 times sine of T over 2. Is that right? Yes. All right, so this is our ODE put in here. Maybe I should have chose a simpler one to show you right out the gate, but let's do the interesting one. You'll notice this doesn't look like the one I showed you in the slide, and that's because our axes are not lined up, right, for a good viewing window. This is often part of the problem, right? If you're looking for a picture, you need to know what window to view it from. So you can come here and open it up a bit. So let's go from 0 to 25 maybe with our T. Same with our U. See what we get. Everybody with me so far? Okay. Anybody not with me so far? Okay. So this looks a little bit more like what we saw previously. And so now what you can do is you can introduce what they call flow lines, which is really like a stand-in for a particular solution. It's an approximation for what a solution probably looks like or close to it using just hard calculations, okay? So you can click somewhere. Let's say, all right, I knew 5, 8 was my particular, my initial condition. I'll click here, and this will give me a solution curve to the best of the computer's ability to do so. You can click to allow multiple flow lines to get a better picture of what, maybe several different initial conditions might do. And, this tends to help you paint a picture, kind of literally, right? You're filling the space up with color, of what happens. What things seem to start from wherever they start, and then they tend to move in this oscillatory way. I'm sure if we opened this up, no guarantees on this, if this will get glitchy on me or not. Okay, not too crazy. I opened up the t-axis a bit. Oh no, that was the y-axis. All right, it's probably going to be a little crazy in here, but starting at t equals 0 or close to 0, we have our initial temperature. Maybe it's a beer, maybe it's a coffee, right? But as time goes on, all these initial conditions tend to move towards this oscillating pattern that what we said the ambient temperature is doing. And doesn't that make sense that now an object is going to kind of follow what the outdoors is doing now that it's taken on the temperature of the outdoors, right? So we can kind of get a lot of insight into a situation just by looking at this graph and plotting a few solutions. Okay, they're also called integral curves. So this is the
flow lines to check like another one.
Good question. So yes, the question was, how do we get multiple flow lines to stay? There is a allow multiple flow lines checkbox down here, right at the bottom. Yeah. Yeah, you got it. So that will allow them to all stay. The more you go with this, the higher the number of maybe arrows you add or segments. The bigger the window. It's going to be pressing on. This is a free tool, so you can easily break it. But it does a very good job to help us kind of get started with looking into problems like this. All right, so this is this tool. We're going to use this during this lab activity.